1.3.
Listen to one today?
Yes, we will listen to part of one today. All right. So in our new packet, we're going to be learning about the normal model. Okay, this is like probably the most foundational concept in this class. So it's totally new idea, but it's very important in statistics to how to understand everything. There will be 3 songs this unit. We're going to learn part of one today. But let's go ahead and first talk about where this thing called the normal model comes from. So what we're trying to do is find the probability of something happening. Okay? And would you agree that, say, the test that you guys took on Friday, do you think there were the same number of A's as the same number as B's and C's and D's and F's? Do you think there were the same number of every single item? Okay? No. If there were, then you could do proportions. You could use a proportion, this thing, x over 100 or whatever, to set up the probability of getting one of these events. Do you think it's more likely that you had less real low, and then you had more in the middle, and then less up in the high scores? Do you think this is what is typically happens more likely on exams?
It's closer than the first.
Okay, this is closer. Okay, good. This is like if you did SATs. In fact, if for the SATs or most standardized tests and stuff, this is what is supposed to happen. You have most of the scores are towards the center, more closely clustered around the center. And then don't you think you have just like very few, perfect scores on the SAT and very few low scores on the SAT, like nothings? So that is what is supposed to happen. So this looks more like a normal curve. What happens is our histograms are based on actual data, and they will help us find the area of a section. All right? What happens is as we decrease the size of the bins, so in this one you had big bins, in this one they were smaller bins. As you decrease the size of the bins, this becomes a more continuous curve, and it looks then more like the perfect normal model. Okay, so that's kind of how it goes from real data to the normal model with nice continuous curve.
And that's with like a lot of bins?
Yes, this is basically like they're infinitely small number of bins. They're just like a ton of bins. Yep. All right. So the normal curve is used to find percents, probabilities, or the proportions of observations that occur. For example, what is the probability that a percent, or I guess it should be a person, that a person has an IQ above 125? Okay? What proportion of the population has an IQ above 105? Well, what we would do is find where 125 falls on the curve, and then we would calculate this area. That would tell us the proportion of the population that has an IQ above 125. All right, so that's where we're headed in this kind of event. So the mean of a normal model is represented by this Greek letter mu, and you guys know it looks like that. It looks kind of like a cursive U. Okay? And then the standard deviation of the normal model is represented by this Greek letter sigma. I've talked to you about that before. It's not a O, and it's not a 0 like when we do outliers. 2 sigma is not 20. Okay? So let's take a look at these following examples here. They are examples of normal models, and I want you to look at the shapes of them. If we say this one is the original, it has a mean of 100 and a standard deviation of 10. Okay? So that's what that one looks like. But I want you to look here. This one has a mean of 100, so the center stayed the same, but it has a standard deviation of 5. What can you tell me about a standard deviation of 5 as opposed to a standard deviation of 10?
5 away instead of 10.
Less varied, more compressed, more closely clustered around the center. Good. Closer to the mean. So envision you have this same amount of data and you have to squish it into a smaller area. That's why this ends up being taller, because you have the same amount of data that you're squishing into a smaller area. Okay, so that's why it pooches up there. All right? Okay, so next, this one would be, looky here. The standard deviation of the original is 10. This one has a standard deviation of 10, but look at what it looks like.
It's different. 130.
Good. The mean went from 100 to 130, so it just shifted over. Okay? And let's take a look at the last one. The mean is still at 100, but it has a standard deviation of 15. So what's happened to that? More varied, flatter, because it's not as closely clustered around the center. Stuff is more spread out. Okay, so this one is more spread out.
So does like the standard deviation, like say whether it's going to be like the height, I guess? I don't know how to explain.
Well, the height is affected, okay, but that's not like the indicator of what the standard deviation is.
Okay.
The height, what is an indicator is how spread out the data is.
Okay.
So when it's more spread out, then the stuff is flatter because of that. If it's closer together, then it's squished up, okay? But the key is more spread out or less spread out. All right, very good. So that's kind of some normal model basics. Now, even though the size of the normal model may change, they all still contain 3 standard deviations above and 3 standard deviations below the mean. Okay, so we're going to look at that picture down here real quick. See this picture? Here is the mean. Here is plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. And then you go down 1 standard deviation, go down 2 standard deviations, go 3 standard deviations. So that is a total of 6 standard deviations across the normal curve. So a total of 6 standard deviations across, so this is a number 6, across the normal model. In fact, there's a business training that a lot of managers and people in businesses, CEOs send their clients or whatever, not their clients, but their managers and stuff too. It's called 6 Sigma. It's because they want the production, they want the data to all be within 6 Sigma. So they don't want outliers way out here past 3 above or 3 below. They want everything contained within 6 Sigma. All right, but back up to here. So the percentage of data contained within the standard deviation stays the same regardless of how spread out or squinched up the normal model is. A normal model is considered standard if it has a mean at 0, okay, a mean of 0, a standard deviation of 1, and the total area or the total percent under the curve is 100%. So that is the standard information. So here we have this. For the nearly normal model, so this is a rule. In some textbooks, it is called the empirical rule. So if you ever go to a college class of statistics, they might call it the empirical rule. But that rule says that if this is your mean, it says that 68% of all the data falls within 1 standard deviation of the mean. 68% of the data falls within 1 standard deviation of the mean. Okay? And furthermore, 95% of the data falls within 2 standard deviations of the mean. And do you remember what an outlier is on a normal model with standard deviation rule? What's the outlier rule for normal model? for standard deviation rule, sorry. For standard deviation rule, what's the outlier rule for standard deviation?
Deviation of one. Or you said,
Mean,
Mean.
median, mode.
Plus
Oh, no.
2 standard deviations makes the upper fence, or the mean minus 2 standard deviations makes the lower fence. Okay, so that means basically things above 2 standard deviations, these ones out here are outliers. Okay, this is the outlier fence, up 2 standard deviations and down 2 standard deviations. So they're saying if you're not in the middle 95% of data, you're considered an outlier. Okay? All right, and then finally, 99.7% of data, 99.7% of data falls within 3 standard deviations. So this is strangely enough called the 68, the 95, and 99.7 rule. Okay, 68, 95, 99.7 rule. And then again, told you some books call it empirical rule, but it recently is more called the 68, 95, 99.7 rule. Okay. So what I want us to do now, oh, by the way, it is possible for observations to fall out here past 3 or more standard deviations, okay? But that's not very likely. And those are incredibly extreme outliers. I mean, if you're out there past 2 standard deviations, you're an outlier. So if you're even more away, then you're like freaky way out there.
You need help.
You need help. All right. So using the information above, let's break down what every section of the normal model is. So this is actually going to kind of take some of your geometry type adding and subtracting areas skills. So I'm going to give you an example. So here's my example. If from here to here is 68% of the data, how much is in each one of these sections?
We just divide 68 by 2.
Yep.
Nice.
So that's 34% and that's 34%. Because those are the same size because of symmetry. Okay? Now, any ideas how I can find the next set?
Divide by 4.
Ooh, nope, because that would be a proportionate.
Oh.
I'm going to take, because if you take 95%
Still.
and you divide it by 4, you're saying there's the same amount in each section. This does not have 34% in it.
Subtract 68.
Ooh, good job.
Cap on it.
Okay, you ready? Watch this. So I know, okay, good. So I know this total across 2 standard deviations is 95%, okay? But let's take out the 34% that I know is already accounted for. So let's do 95 minus 68. And how much do I get? Okay, so that means 27% is left between this section and this section. Those 2 sections combined equal 27% because 68% is already accounted for.
13 and a half.
Good. So
No,
if you
question.
divide 27 by half, that means 13.5% in each one of those sections. Okay? So this one has 13.5%. And this one has 13.5%. All right. Now, could you use that same concept with this 3 standard deviations out
Yes.
to 3 standard deviations out?
Or you
How much is 3 standard deviations out supposed to contain?
97.5 or 99.7.
So take 99.7 and subtract out the part that you have already computed. How much have you already computed in the center?
95.
You've already computed 95%, so take that out. Okay,
So 2.35.
yep. So that means 4.7 is split in these 2 halves. So 2.35% is in each one of these sections. Okay? And now we're almost finished. We're almost finished. I want you to figure out what's left over in these little teeny tiny sections to negative infinity and to positive infinity. It's going to be a very small decimal, so figure it out. So I'll wait for a sec. Wait. Okay, good. So you take your 100%, subtract away the 99.7. That leaves you with 0.3 that needs to be split between these two groups. And so 0.3 being split between those two groups makes 0.15%. So that's actually a very small amount. That's only like a little bitty bit of 1%. 0.15%. Okay, and that goes from here out to infinity. Okay, so those are your sections. Those amounts are always those amounts. Those stay that amounts. No matter how spread out the curve is or how squunched in the curve is, between one standard deviation, from here to here, from the mean to one standard deviation is 34% of the data, and so on. All right, very good. Moving on. So let's take this and let's put some context to it so it can kind of start making a little bit more sense in the real world. So SAT scores are distributed nearly normally with a mean of 1,500 and a standard deviation of 300. So I want you to put those values on this. So put the values on this curve. So like the mean is, what did it say, 1,500? So that must be the SAT when it had the writing part in it or something. So put your 1,500, and then how would I get one standard deviation up?
Plus.
Yes, plus what? 300. 300. One standard deviation, guys.
Wait, how'd you get 3?
Because one standard deviation is 300 points. So if you are one standard deviation up, you made a score of 1,800.
1,800.
If you are two standard deviations up,
2,100.
you made a score of 2,100
24.
and 2,400. Okay, let's go down. One standard deviation down, you made a score of
1,200.
1,200 and so on.
960.
Okay. All right, so those are the values that you would have gotten. Okay, so let's see here. So we're going to talk about, do they tell you on your SAT score what percentile you're in? Do they say you're in this percentile, like the 85th percentile or anything like that?
You can find it, but they don't like tell
They
you.
do that with, like,
Like if you go online and look,
Okay.
then you can.
So they don't tell you, but you can go online and find it out. Okay, cool. So what a percentile means. Also, when you go to the doctor, if they're, when you were growing up, every time you go to the pediatrician each year, they measure your height and weight and say what percentile you are in for your height and weight. So percentile means how much is below your location. So if you got an 1,800, which is one standard deviation up, then we could tell what percentile you are in. So let's think about that for a minute. How much percent is from the mean down? So this is 50% below the mean. How much was between this one and this one that we figured out a minute ago?
25.
25.
No.
Oh, it's 35.
34.
Look here. 34 was from the mean to one standard deviation up 34% because the middle 68, okay? So that means this is 34%. So what that means is if you got an 1,800, you are in what percentile?
80.
You are in the 84th percentile. Because a percentile is how much you have below you. All right, moving on. I think this next one covers that information. So it might help us if we go ahead and put these percentages back in here. So let's do that real quick. So I'm going to draw this picture here with put our percentiles we figured out a minute ago in here.
What page is that on?
This is the page we were just on. The percentiles page. It's up at the top. Okay. So let's do this. You guys did this a moment ago. 34, 34, 13 and a half, 13 and a half, 2.35, and 0.15. Okay. All right, so using that information, we're going to answer these questions on the next page. We did the first one. What percentile of students score less than 1,800 on the SAT?
That's 50.
So what percent was below an 1,800?
It's 50. Because you just said it's 50 a minute ago.
Then add those up.
Yeah, remember 1,500 and down was 50%? And then from 50% to here was 34%. So what percent is below an 1,800? 84%. So 84% is below an 1,800. Okay. What percent of students score above a 1,500? Where is 1,500 located? It's the middle. So if it's the mean, then how much is above it? 50%. How much is below it? 50%. It's right in the middle. So this one is 50%. Okay, so I'm going to give you a few moments to figure those out on your own, and then we'll come back together and see how you did.
Oh, whoa.
Okay. Oh, wait a
I got a
second.
Callaway. Check the Zoom.
You got a cluster?
Oh, you Kevin.
I got so mad and I called Callaway cluster. Why did you do that?
You called Kenny Cluster? Have you ever had a pillow fight?
Hey,
I feel like ours so.
Wait. How'd you get 83.85 for E?
Okay, so from 1,200,
Because isn't it the same thing as?
from 1,200 to 2,400.
Wait, wouldn't 2,400 be a perfect score though? So wouldn't that be the 100%?
Ah, I see what you're saying.
Yeah.
Okay, that's a good point. Yeah.
I
Gotcha.
can see where that.
I see why you would say that. We're going to, I mean, because you can't get a higher score than that, so that kind of messes things up, I guess. I'm kind of, yeah. But if it was on a normal model, and there was higher scores up here, then yes, it would be that. You would not include that 0.15. Yes. Yes.
So it's 83.85 for both.
Yes. All right.
Why is?
Because it's not
You
included.
can't get a better score than 2,400.
They included it at 20. They included the top 20. They didn't include this because they said you can't get better than 2,400. But if you could, then you know there's that out there and stuff. Yeah.
So it is 83.
It's 83.85%.
So there's no upper outliers, is that right?
So there can't. No, there can be upper outliers between 2 and 3
Wow.
because above the 2 standard deviations is
Oh
an
yeah,
outlier.
I guess. Right.
Okay. All right. Now moving on. Okay. So here we go. Now let's talk about this situation. How many of you guys have taken the SAT and the ACT? Anybody take both? Oh wow. Okay. So if you take both of those, then then we have 2 different grade scales, right? One of them is based off a totally different number scales than the other. So let's take a look at this. SAT scores are distributed nearly normally with 1,500 mean and standard deviation 300. But the ACTs are nearly normally distributed with a mean of 21 and a standard deviation of 5. A college admissions officer wants to determine Which of the two applicants scored better on their standardized test with respect to the other test takers? Pam, who earned an 1800 on her SAT, or Jim, who scored a 24
Oh, yeah.
on his on his ACT. There's a new packet over there, Kirsten.
Wait,
Is this one of y'all kids? Duh.
Yeah, because
Oh.
Pam's got a test on
I guess so, I don't know. All right, so let's take a look at that. So the issue is that, we have two totally different scales. How are we going to compare where Jim scored compared to where Pam got relative to the other people? Any ideas?
We are gonna go through and find the percentile there.
Oh, nice. I like that. You could go through and find the percentile for each one. Okay, good. That is that is true. You can definitely do that. That's a good idea. We could do one step less than that, which is something you haven't learned about that I'm going to tell you about right now. At the top of the next page, we could find their Z-score. And a Z-score is a number that tells me how many standard deviations they are above the mean. So see, I can tell is Pam more standard deviations above the mean, or is Jim more standard deviations above the mean? Just from looking at this picture here, if you just by looking at the picture, how many standard deviations does it look like Pam is above the mean?
One.
Okay, so she looks like she's one standard deviation above the mean. How about Jim? And he's probably more like 2/3 or something, yeah. Or 3/4. Okay, so based on those numbers, who did better relative to their peers?
I'd say Pam.
Pam did. Pam did better because she is more standard deviations above the mean, which would mean that if we found this area below her, which is that percentile, then she would be above more people, a higher percentage of people. All right, so here we go. A Z-score represents how many standard deviations a piece of data is away from the mean. These are called standardized Z-scores. A Z-score is an observation, is the number of standard deviations that falls above or below the mean. Okay, I've said that a whole lot. So to get a Z-score, what we do is we do the X value, that's the context value, like her 1800 or his 24, minus the mean of that section over the standard deviation. Okay, so we're going to go Z equals X minus the mean over the standard deviation. X minus the mean over the standard deviation. Yes, that is a song.
Let it rip.
So let's see here.
Yeah.
Yeah.
Inverse